more about the real neural networks, because I think this is interesting, but also about modeling these real neural networks. So obviously neuroscience is a huge field, so there is no way we can say something complete or even some kind of broad overview in 2 hours. It's just impossible. So I will concentrate just on a few aspects which are related to historically to statistical physics, and especially what I will be interested in is let's say recurrent neural networks. That's an aspect I have not talked about so far. So essentially what we have, you can imagine you have a set of neurons which are connected to each other through some couplings. So here I have some variables, activity variables SI, which I will consider to be 0, 1, but it could be something more complicated. I mean, if we want to discretize, let's say, some continuous activity, for instance, in more than 2 levels, and some interactions, Jij. And there will be some kind of nonlinear dynamical rules telling us how the activity variables are updated with time. And we can represent formally what is going on here as a point evolving in a very high dimensional space. So I'm considering the vector of activities, the vector of SIs, which is an n-dimensional vector if I got n neurons. And the activity at time t is evolving according to some trajectory. And of course, what we would like to understand is what kind of trajectory we get and so on. So what I will focus on today is just one specific aspect of that, is the long-term dynamics, especially in the case where what we end up with are fixed points of the dynamics. So in that particular case, we have what people call attractors, so which may be different fixed points, different activity configurations here. If we have 0-dimensional attractors, just specific configurations, and maybe if the network is stochastic, we'll have some fluctuations around the fixed point, otherwise 0 temperature, it will be really a fixed point. And there will be Bayesian of attraction separating the different fixed points. Depending on the initial condition, will fall onto one of these fixed points or the other. So this is a situation that people have been considering for a long time, but you could have more complicated or more interesting situations where the fixed points, or let's say are not 0-dimensional, I mean the attractors are not 0-dimensional attractors, they are not fixed points, but they are higher dimensional objects. So for instance, you could have d-dimensional attractors. So just to avoid any ambiguities, I'm not saying that the dynamical attractors is a cycle here. This is not what I'm talking about. It's a set of fixed points, and depending on the initial condition, you may end up anywhere along this manifold. So for instance, I start here, then I will have some trajectory, I will end up here, and this is a fixed point. Maybe starting from a different initial condition, I will start here, I will stop here, and so on, okay? So you could have here a 1-dimensional attractor, but it could be any kind of dimension d larger than 0. And there will be also Bayesian of attraction between these attractors. And one aspect I will be interested in is to show you and try to convince you that this kind of phenomena happens in real neural networks. We don't have exact proof, but there is indirect evidence for that. And one aspect which is particularly interesting is, there are 2 aspects I will take time and to discuss. I mean, I will discuss to some extent, is how we can go from one attractor, one d-dimensional attractor to another one. So what are the processes? So that's an interesting statistical physics problem, and we'll see how this is done in experiments. And also, how do we select one particular Bayesian of attraction with respect to another? So how the different inputs to the systems, which define essentially the initial condition on some drive, external drive, are selecting the different attractors. Okay, so this is what I want to talk about, and show you also different kind of experimental techniques and experimental results on this aspect. And one question I'd be interested in also, because we are the whole lecture is about learning, is how actually can we program, can we engineer some particular attractors by engineering the different connections between the neurons in the network. So suppose you want to realize these attractors, how do you want to choose a Jij in order to do that? What is the maximum number of attractors you can actually define by a careful engineering of a Jij, and so on. So this problem actually was, in the case of 0-dimensional attractors, this particular case here, which is the simplest one, was actually studied a long time ago in the Hafiz model. So I will, in 1982. So John Hafiz gave a practical way of building a model with multiple point attractors. So I will briefly remind you of the model, about the model, because maybe some of you are not so familiar, so but it's just an introduction. And then I talk about other things which are more interesting in, now, I mean today, about d-dimensional attractors. So I'll talk about two models. One is Hafiz Model, which is actually older than Hafiz Model, which considers the case of a single d-dimensional attractor, where d is, in his paper was equal, was equal to 1, but actually it can be anything which is larger than 1, or equal to 1. And then a more interesting model, which actually was some kind of mixture between Hafiz Model and Hafiz Model, first done by Samsonovich and Magnoton in 1997, which is, I don't think it's well known in statistical physics, where multiple d-dimensional attractors can be encoded in the same network. Okay? And then I talk about experimental evidence for these attractors. Okay, so just as a reminder to start with, what about Hafiz Model? So I guess most of you know Hafiz Model, probably all of you, right? All of you, or no, not all of you. So okay. So Hafiz paper is this one in 1982. So basically, the goal of this paper was to show how a very simple model of interacting units, very simple binary units, 0, 1, was able to was having interesting emergent collective properties, in particular to build some auto-associative memory. So I will define in more details what the model is doing, but essentially the idea is that you have different ways of memorizing information. One way is having, for instance, a table, an array, where you put in different places. Let's say place number 1, you would put some number, place number 2, another number, or you put images and so on, and then you can recall, for instance, the item in place number 12. Okay, this is what people call an addressable memory. But there are other ways of memorizing things which are maybe more interesting from a biological point of view, which are auto-associative memory. So, for instance, you get only a partial information, a partial, just a part of your item you have memorized, and how can you actually reconstruct the whole item? So this is actually what this model was trying to do, and it was doing it in a very efficient way, in a very robust way. That means this is the whole memory is encoding in a network, and if you can, for instance, you destroy or remove a large number of connection in the network, you increase temperature and so on, then the network is still working to a large extent, okay? Up to some catastrophe, obviously, if it goes too far. Okay, so how is the model? So the model is an extremely oversimplified version of real networks, on real neural networks. So in the model, each neuron is an Ising spin. So originally in the model, they were -1 + 1, but it could be 0, 1, doesn't change anything. And essentially, the idea is how, I mean, the interesting, so what does it mean? It means 0 can be thought as a neuron which is silent, and 1 as a neuron which is active. So what about real neurons? So the activity variables in a neuron usually is measured as a function of the potential, the difference in the potential between the external part and the internal part of the membrane. So a neuron is a cell, and so you will have two different potentials on the upper part, let's say the outer part and the inner part of the membrane of a cell. So typically the difference of potential is about -70 millivolts when the neuron is silent, and when the neuron becomes active, then there is a very sharp wave, electrical wave, which is actually emitted and propagating along the axon, which is the output of the neuron, so the external part of the neuron, which is connected to other neurons. And this sharp wave is localized in time. Its duration about 1 millisecond, typically. It depends on the organism. It can be larger, it can be smaller. And then it will propagate along this thing here, along the axon. So if we bin the time into small time bins, a few milliseconds, for instance, the neuron can be either in the red state here, you would say it's silent, so variable would be 0, or it could be in this state here, and we'll say it will be active, so the state will be 1. Okay? So that requires some kind of discrete time definition, so some appropriate binning of a continuous time. Now, what about the dynamical rules? So if we have neurons here, these neurons, which receives different inputs coming from the different other neurons. So here you have another neuron. So this neuron may be active or silent, and it will be connecting to this neuron here, which I am interested in, through some coefficients, interaction coefficients, which are called synapses. So the biology of a synapse is very complex. I won't talk about that today. But the important thing is that when this wave is propagating and arrives at the end here, of the axon here, it can actually elicit or produce a small electrical, small change in the potential of the second neuron here, okay? And the intensity of the change is actually given by the strength of the synaptic coefficients here, the synaptic interactions. And this is modulated, okay? So it can be 0, it can be positive or negative, depending on the type of the neurons. So essentially, this is shown here. So here you see the same thing as here. You see the difference of potential between the external part and the internal part of the membrane of this neuron. And as an electrical wave is propagating along the first neuron here, it arrives here, then it will produce, through some complicated mechanism here, a small increase of a difference of potential, or a small, so it will increase or it will decrease depending on whether the coefficient here is positive or negative. Okay? And the important fact is that this neuron is actually connected to many other neurons. So if many inputs arrive at the same time, then they will sum up and they will exceed some threshold, and then they will a wave like that, which is a spike, an action potential, will be emitted by this one. So essentially, the dynamical rule is representing that. So if we have the states of activities of all neurons here, A, B, C, and so on, then these activity variables, which are 0, 1s, are summed up and weighted by some synaptic coefficient, J, JB, and so on. They are compared to some threshold here, and if the sum is above a threshold, then the neuron becomes active. Otherwise, it remains silent. Okay? So this is the idea of a model. Okay, so now we have we know everything about the dynamics of the model if we are given the initial condition and we are given the synaptic coefficients, right? Everything is well defined. The question is, how do we define the synaptic coefficients? So what Hafiz did is that he was inspired by some old work from Donald Hebb at the end of the 40s, which was very influential and purely theoretical work. And essentially, the idea that Hebb put forward is that neurons which fire together wire together. So contrary to what we have in physics, where the interactions actually are given in the Hamiltonian, for instance, and then you study the dynamics of a system, here the interaction will be modified during the dynamics. And there is a feedback of the activity of a system onto the interaction. So the Hamiltonian is actually modifying itself depending on the dynamics it had produced at the previous time. Okay? So it's a very important principle. And the idea is that neurons which have a tendency to be active will together in synchronous way, then we have a connection which will be strengthened across time. And if they have no synchronization in the activity, then the connection will decrease. So this is obviously an oversimplification, but there is some evidence I already talked about in the previous lectures for this mechanism, which actually came a long time after this very influential book. Okay, so how does that work? Now this is the model, complete model. So suppose you want to memorize a certain set of configurations. So the psi mu will be these configurations which you want to memorize. So I is the index of the neurons, which runs from 1 to n. Mu is the index of the pattern, the specific configuration you want to memorize. It runs from 1 to p, and they will be plus or minus 1. So plus 1 is the neuron is active, minus 1 is silent. So according to Hebb's rule, the idea is to propose that the connection matrix, an adequate connection matrix, is Jij equal to the sum of a mu psi j mu. And then we can update the dynamics of the network according to the what I've shown in the previous slides. This is exactly the same dynamical rules here. And the question we ask is whether actually if we run these dynamics for some time, whether it will reach some fixed points and whether the fixed point will be close or not to these patterns here. So why this may work, actually, is in the case of a single pattern, you know why it may work, because think, for instance, of the Curie-Weiss model. So in the Curie-Weiss models, which is a mean field version of the IZ model, where all the Jij will be equal to 1 over n, you know that if the temperature is low enough, or let's say if J is large enough, which is the same thing, then you know that the state of a network will be magnetized. So that means that the sum over I of Si, which is the magnetization, will be larger than 0, or let's say different from 0, I mean, if you go to low enough temperature. So in this sense, even if there are some thermal fluctuations, the network will organize around some state of activity which is close to the pattern 1, 1, 1, and all ones, right? So this is one particular case example of a pattern psi. Now, obviously, there is no reason why I can choose this only. I can multiply this thing here by anything which is just a global gauge. This is called the Lattice model. Jij is j over n sigma I, sigma j, where the sigma I and sigma j are plus or minus 1. Okay? And you will get exactly the same thing just by a change of variables. And of course, now the magnetization will be something like that, right? And for the same reason, it will become larger than 0 at the same critical temperature. But now what you have memorized is a pattern of activity which is more interesting. Psi is actually the sigma 1, sigma 2, sigma n. So the idea of the Hafiz model, behind the Hafiz model, is actually if the different configuration sigmas or psi here in the notation here are more or less orthogonal, then maybe you can just pile onto each other different Lattice models, and they will not interact too much together, and that will work. Okay, and in fact, this can be shown. It was that if you look at the dynamical equation here, this is just a 0 temperature updating rule, which is minimizing this energy function here. So we recognize exactly the Ising model with some local fields here, which correspond to a threshold, to the local thresholds. Okay, so we know that as the dynamics goes on, then depending on initial condition, we will converge to a local minimum. And the question is whether the local minima of this landscape are correlated or not with the patterns we want to memorize here. And the answer was found by Amit Gulfan-Sompolinski. I mean, it was just already empirically found by Hafiz and then demonstrated using spin glass theory that if the number of patterns divided by the size of a network is smaller than 0.14 or something like that, or close to it, then there exist local minima which are close to the local patterns, very close to them. Otherwise, there is no such local minima. Okay? So it was just a reminder about the Hafiz model. Is it clear? Okay, so we have this idea that many different fixed points can be encoded by an appropriate choice of a Jij. And there is also the notion of critical capacity. You cannot put too many of them. The maximum number depends on the size of the network. So the two ideas are actually important. So now I'd like to move to a more, let's say, interesting kind of attractors, which are these finite dimensional attractors. And so they appeared in neuroscience for different reasons, and especially after the discovery of particular kind of cells, of neurons, whose activity is correlated with some sensory inputs. So the cells which were first interesting in this context are called head direction cells. So head direction cells are cells which are recorded in rodents and also in other organisms, in other animals, but first in rodents, where actually the activity of a cell will depend on the angle of the head of the animal with respect to some absolute direction. Okay, so that means that there are cells in the brain of rats, for instance, which are active when the angle of the head of a rat with some direction here is equal to, let's say, 25 degrees plus or minus 10. And if the animal is actually looking at or pointing his head in another direction, then this cell will be almost silent. Okay?
How is this spatial direction determined?
Okay, so actually you have a whole population of different cells, which code for all possible angles here. And this direction actually is usually one direction of the environment, typical a wall or something like that, some kind of absolute reference direction, which makes sense for this particular environment. Okay, so it's learned, and then people see that when they do the experiment. So I won't talk about that. This is so historically that was very interesting, and this is still very interesting. But I'll talk about other kind of cells whose activity is correlated with the environment and with the action of the animals. And this is related to the representation of space in the brain, because there were many interesting experiments in the past years, and this is still going on very much. And I will show you different kind of experiments, maybe 10 of them, so you can see you have some kind of overview of what is going on in the field, which I find fascinating. So what is the starting point? So the starting point is some experiment by O'Keefe and Dostoevsky in 1971, and O'Keefe got the Nobel Prize for that in 2014. And O'Keefe was particularly interested in the hippocampus. So the hippocampus is a region of the brain. Here you see the brain of a rat, a drawing of the brain of a rat. So this region contains about 300,000 neurons in rats, and in humans it's about 2 orders of magnitude more. Okay? This is present in all mammals and to some extent in all vertebrates. To some extent because they are not exactly the same. I mean, there are evolutionary related parts of the brains, but they are not exactly the same anatomical description and so on, properties. But anyway, so this is something which emerged a long time ago during evolution. So it has been known for a long time that the hippocampus is a very important region for the formation and the memorization of short-term memories. So for instance, there have been very well-known cases of patients which actually had some brain damage in this region, and they were unable to form new memories, to memorize new things. But still, they could remember really well past memories. Okay? So actually, O'Keefe and his collaborators in 1971 were the first one to put some electrodes in the hippocampus and measure the activity of the cells there. So it's a complicated story, but just to make it short, and then I'll go to more details in the following, what they showed is that there are some cells in the hippocampus which respond to position in space, and they are called place cells. So what does that mean? It means the following thing. That means there is one particular cell here in the hippocampus of the rat, of the mouse, or whatever, which will be active when the so this is the environment, for instance, a circular arena. When the mouse is somewhere here in this blue region, the cell will become very active, and then if it exits this area, then it will become silent. Okay, let's say its activity will be much more stronger here than in other places, in other spots in the environment. There is no physical boundary here. Okay, it could be just an empty space. But there is a region, which is called the place field, where this cell will be very active. If you take another cell in the hippocampus, then you will see essentially the same phenomenon, but this will be related to another place field. So this cell A here will be active in another place. Okay. So this discovery was important because it immediately led to the idea of what O'Keefe called the cognitive map. That is, maybe these cells are responsible for the way we code for space in our brain. And what we need actually is a representation of space, because we need to be able to move and to make decisions according to where we are in space and what we want to achieve, where we want to go. So I will talk more about that later on, but I just want to show a few properties of these place cells which are important. So first of all, visual inputs are very important for the formation of place cells. They are not necessary to maintain the activity of place cells. So here is a quite old experiment from the 90s, where you see what is going on for 4 different environments on 4 different cells. And so what the people did here in this experiment by Quirk and collaborators is that they measured the activities of one particular place cell. And you see these colors here, which corresponds to where the place cell was active and so on. So the place cell is active when the rat is close to this side of the border of the environment here. Then this is recording when the light is on. You can switch off the light. You see a slightly more, let's say, random activity, but still very much concentrated around here. Switch on the light again, and you get exactly the same spot. That means even in the absence of any visual stimulus, the animal is still able to maintain a correlation between its position and the activity of a cell, which is a highly non-trivial thing, right? And the way this is done is called a mechanism which is called path integration. That is, the animal is able to integrate its motion in order to maintain, some kind of correlation between where it is and where a cell should fire. So I'll talk again about this because that's an important thing. So far, the only important thing here I want to mention is that you can have a place cell without any visual stimulus. It's not only that the animal is seeing something and then maybe it recognizes some spot and then the cell will fire. It's more complicated than that, much more complicated than that. It's the first thing. Another thing which is very important, and I like very much this experiment by Buzzaki and collaborators, is this one. So here you have a rat which is moving in one maze, and the maze is just a single corridor, so it's a very simple environment, a one-dimensional environment. And there are 2 water pots at the 2 extremities of the maze, in the blue dot here and in the red dot. So what the rat is doing is very simple. it runs from one extremity to the other extremities, then drinks some water, takes some rest, and then runs the other way, in the other way, and does exactly the same thing again and again. A rat's life, okay? Which is, okay, interesting. Okay, so what people do, they measure the activity of place cells, and actually, you know, that was done in 2007, and the big jump, technological jump between the 70s, when O'Keefe did his first experiments, and now, essentially, is that now we are able to put more than one electrode. So people can put more electrodes, so they can measure more cells. And what you see here, you get 13 place cells, which were recorded simultaneously in the hippocampus of this animal. And so look at this drawing here. So what you see here is time in seconds as the rat is moving from the red to the blue dots. And you see here in this inset the velocity of the rat in centimeters per second. So the rat is at rest here, at rest at the end, and then it's running from the red to the blue dot, okay? And during this motion, during this run, you see a sequence of place cells which are firing one after the other. So here, each vertical bar corresponds to a spike, this, you know, very sharp localizing time wave, electrical wave I mentioned, emitted by the first cell, the second cell, the third cell, and so on. So obviously, when people put the electrodes in the hippocampus, the cells do not come in rank, nicely in rank, okay? There is a large amount of processing which is necessary in order to get this data. These are not the raw data. The raw data are the electrical potentials, and then people have to find exactly at what time each particular cell is firing. This is an interesting thing I'm not talking about, which is called spike sorting. And then the experimentalists rank the different cells according to the position of a place field here, from the leftmost to the rightmost place fields. So as the rat is moving, you see that the cells fire one after the other, because they cross the different place fields. The rat is crossing the different place fields, one after the other. Okay, so far so good. But now look at what is going on in the red and the blue windows here. So this is when the rat is actually drinking water and taking some rest. So what you see is that on a very short time scale, which is about, you know, a few hundred of milliseconds, which has nothing to do with the physical motion, which takes place on a few seconds, then exactly the same sequence of cell firing is taking place. So before actually the physical motion, the rat is planning to move to the other extremity, and then the sequence of firing, which is going to take place during the physical motion, is actually taking place. And the interesting thing is that this time scale is, you know, shorter about factor 20 compared to the real, physical time scale. In fact, even more surprisingly, if you go at the end of the thing here, of the motion, you see exactly the same sequence in the backward order. So the cells are playing back this motion here, but starting from the last one and ending up with the first one. And this is typically, so that's something that people call backward replay. And it's typically what is found when an animal plans a task or plans a motion, and then the motion of the task was successful. So it's a way that people think that actually replaying this activity through the Hebb mechanism I was mentioning before is actually strengthening the connection. That was good planning. Just do it again. Okay, so what I'm saying is a kind of caricature, but this is basically the main message. Yes?
How do you know that it's actually just replaying going to the right and not planning going to the left?
Oh yes, because actually it takes some time, you know, before it does exactly the same thing, and then the order, you see, the ordering is not the right one. Well, I mean, you mean when it goes there?
Yeah, because you said
no, it will be the right one. Sorry, I made a mistake. It will be the right one, but it takes some time because it takes some rest for a few seconds because it goes there. Well, this thing is exactly when it essentially arrives at rest. Yeah, sorry.
What's the upper line?
Oh, the upper line, I think this is, I have to check in the paper, but I think this is EEG. So people measure some kind of average activity with the, and okay, so there is something important also here, is that there is, so the activity of the hippocampus is modulated in rats or in rodents by some rhythms. So one rhythm which is very important is called the theta rhythm, which is about 8 hertz. And it's believed that this underlying background rhythm is actually very important for strengthening connection and all the synaptic modification. So it was at the basis of many models, and then people did the same experiment in bats, which I will show you, which are also mammals, but then they have a third dimension, so they are very interesting mammals. And then there is no tetarism in bats. So it might be that tetarism is very important for rats, but it's not a fundamental universal mechanism for learning in all mammals. So that's...
Sorry, what's happening in the blue area is also related to the memory consolidation that or it is a different thing?
Okay, it's a different thing. Memory consolidation is supposed to be a transfer of information from the hippocampus to other regions in the brain, in the prefrontal cortex. And it's certainly true that you can have replay in the hippocampus, which is necessary for activating in the right order the corresponding sequence of cells in the PFC. Okay. And in fact, it's also this kind of things also correspond to some specific rhythms, which are called sharp waves, so very strong excitations in the hippocampus, which are also found during memory consolidation. But the animal is not sleeping in any way here. I don't think so. I mean, it's just. But I mean, replay is also important for memory consolidation, definitely. So what is important here, I wanted to insist on, is that the time scale here you see has nothing to do with the physical time scale of motion. So that means that the dynamics here of a place cell is not generated by some input changing across or during the physical motion. It's typically, and that suggests very strongly that actually this sequence of activation is internally created by the network. So network is actually formed in the hippocampus and without any inputs, or actually no visual inputs, or no inputs coming from physical motion, then the whole sequence can be played. So we need some way of generating internally, only through the network activity, this kind of activity. Only through the network, this kind of activity. Okay? So one obvious thing which will be useful in the following is that if I look at the neural activity here, so I have a population activity of 13 cells. So if at any time, or let's say in a short time being on a few milliseconds here, I look at what cells are active and what cells are silent, I can say something about where the animal is. It's obvious, right? If these cells are active, then probably the animal is at the beginning of a track. If these cells are active, then it's in the middle of the track. So a lot of people have been doing decoding of position based on these ideas. So I will need that in the following, so let me just explain how it works. And this is very simple decoding using the neural activity. So again, here you have an animal moving along a 1D track and different cells which are activated at different places here, different place fields. So what we can do, for instance, to decode the position given the activity is measure, for instance, these things here. So these are called rate maps, and this is just measuring the average activity of place cell number 1 as a position of the animal along the track. So you see here you have, this is blue everywhere. Blue is a color code for very low activity, essentially 0 spike emitted. And when the animal is somewhere here, then then you get a very strong activity, so maybe a few tenths of hertz. This is the maximal activity of place cells. And here in the yellow region, maybe it would be just 5 hertz or something like that. Okay? And you can do that by measuring the position of the animal and at the same time the activity of the neurons. You can establish this kind of maps, the rate maps. Once you get the average activity as a function of a position for all the neurons, then you can do very simple decoding in this way. So this is a standard way of decoding the position, which I'm now explaining. So if you look at one particular place cell, so for instance place cell number 1, then you can assume, for instance, that the cell has some kind of Poisson activity, which is obviously an oversimplification, but it's something we can do. So conditioned to the position X of the animal, the number of spikes which are emitted by place cell number I during a time being, which is time being number t, okay, will be simply given by this Poisson law, where so the average number of spikes will be simply the firing frequency times the width of the time being, delta t. And then we have this thing elevated to s, which is an integer number, 0, 1, 2, 3, and so on, divided the factorial, and then you get the exponential minus fi delta t. So it tells you how many, essentially that's the probability distribution of the number of spikes in a time being of cell I. Now, so first of all, there is no reason why actually this is true, that it's a Poisson law, and there is some evidence that it's not Poisson. I'll come back to that, but this is a reasonable model. It's a simple model, at least. Then second step is to assume, for instance, that the place cell activities are independent from each other, okay, which is another assumption that can be strongly criticized. So if this is true, or at least you assume this thing, then you would say that the probability of the whole vector of activities for all the i's, all the place cells i's, conditioned to the position x, will be the product of this Poisson law distribution. Okay? And now what we can do is to decode the position, and there are different ways of doing that. So for instance, if we look, we measure the activity, in time in number t, we have all the cells, which are, this cell emitted 2 spikes, this one 0, 0, 2, 3, and so on. Then we can find the value of x which maximizes this. That's called maximum decoding. Or we can do something a little bit more subtle, where we have some prior information about the possible position of the animal, and we will maximize the product of the likelihood here times the prior information about x. So for instance, a very simple and reasonable prior is that in between 2 time means, which are separated by a few tenths of milliseconds, the animal cannot have jumped from one side of the box to the other one. Okay, that's not possible. So what you can do is you say, for instance, that the 2 positions which are decoded at time t and t minus delta t should be close to each other. So you can put some kind of Gaussian prior where d here is the average velocity of the animal. That helps if you don't recall many neurons, and then there is very little information to infer the position from. Okay. So you see how it works? Okay. So that's a very simple way to decode. So for instance, just to show you the accuracy of this technique. So these are some decoding we did for. So this is one specific region of a hippocampus, which is called CA1. So it's an animal which is moving in a 60 centimeter by 60 centimeter box, and 34 cells were recorded. So these are data by Karel Jezek and collaborators, who is in Pilsen University. And so what you see here, so this is as a function of time. You see the position x and the position y, so the 2 coordinates in the box, x and y, as a function of time. And there are 2 curves. One is the true position, which is the red curve, which is recorded by a camera, so you know exactly where the animal is. On the blue one is the one which is inferred by the formula I've shown you. This one, when you take this prior. So you see, with only 30 cells, you can have a pretty good reconstruction of the position of the animal. There are hundreds of thousands of cells in the hippocampus. Okay, so it's nothing. What is recorded is nothing compared to the whole population. So that means that there is pretty good information about the position. Yes.
It's two dimensions, and what are the shape of the place field, like circle?
So the shape of a place field are essentially this kind of. Okay, I will show you. I have. Okay, let me show you. I can. I'm doing what I should never do, right? I'm spoiling everything. So this is typically what you find. So this is the shape of a place field. Typically some kind of, circular bump. It's not circular. I mean, it's a little bit, usually some kind of ellipse, but more or less the aspect ratio is the same in 2 orthogonal directions. Usually, most place fields are connected. It's rare, but possible to find place fields which have 2 different disconnected components. It's okay? Okay, so actually we are just saying there are place cells, so they code for position, right? Okay, so based on these discoveries, actually, people thought that actually a model which was invented in the context of head direction cells could be very useful to actually represent what is going on and to find a model of a network which can actually code for position and is plausible for this kind of activity. So I will introduce this model in a statistical physics way. And you see the analogy with Hafiz model in the case of a single pattern of activity. Okay, so what is the model? So we have neurons. We have a set of neurons which can take 2 values, 0, 1, whether they are silent or active, and we'll have interaction Jij. So in the case of a Hafiz model, in a single pattern, so this Hafiz model, this Lattice model, the interaction were just a function of the activity configuration you wanted to memorize. Okay? But now what we want to memorize is not a single activity configuration, it's a space. We want to memorize some kind of spatial map of the space the rat is moving in. So what does that mean? So the model, simple way of defining the model is the following. Take two neurons in the hippocampus. So this is my virtual hippocampus, my neural networks. There are two neurons, the red and the orange one. The green and the orange one. These two neurons will have place fields, okay? So for instance, this neuron will be very active when the rat is here, and this one when the rat is here. So I'm assuming that there are some kind of circular place fields, very simple. So the only thing which matters is the distance between the place field centers. Now what is going on? The rat is actually moving in the space. So this is the trajectory, so you can look at the red dots, and this is the trajectory of a rat, okay, during the exploration of the environment, the first time the rat is put in the environment. These two place cells are never active together, right? Because the orange one is active when the rat is here, and then the green is silent. So nothing is going on in between. If I look at the Hep's mechanism, neurons which fire together, wire together, then nothing will happen. But now assume that the distance here is smaller and there is some overlap between the two place fields. Then there are positions in space where the rat is, and the two neurons will have a tendency to fire together. So it's a mechanism to strengthen the connection. So the idea is to make a connection, to build a connection, which is a function of the distance between the two place fields, centers, which will be strong and positive at short distances, and maybe zero, or let's say something which is independent of distance at large distances. We'll see whether it's zero or some kind of negative number. It doesn't matter very much. Is it clear? Okay. So the idea is actually to build a kind of connection matrix, which is, let's say, the adjacency matrix between the place field in the physical space. So at the end of this learning process, and this is just hypothetical, there is no experimental proof of that so far, because nobody has measured how the connections were evolving when the rat is put in a new environment and how they are formed. This is not known. But it's plausible that something like that is going on. Then you will have a neural network whose connections are exactly the adjacency, build the adjacency matrix of these place fields. But of course, you have to be careful. This kind of drawing is nice, but the reality is this one. The reality is this one in the sense that there is absolutely no connection between the real position of neurons in the hippocampus and the positions of the place fields in the environment. They cannot be, because the same network has to be recruited for many different environments. It would make no sense. And in fact, when people put an electrode in the brain, do I have it here? No, I don't have it here. Imagine you put an electrode here, and you will measure the cells, the activity of the cells which are close to this electrode, and they will code for place fields which are scattered all over the place. So the neurons are close to each other in the hippocampus, but the place fields are completely random in space. So actually, these two graphs are just isomorph. Okay, it's isomorphic. This is the same graph. I just moved the points around. Yes.
Sorry, but when you go to a new environment, do you need to redo all the connections, or can you keep the same connections and take place fields according to positions in this new environment?
So the connection will adapt. I mean, this is the hypothesis, okay? But first of all, not all connections are possible, because there are some new experiments where people have measured the density of connection in the hippocampus, and this is very sparse, okay? So that means the number of connections which exist is very weak, but then they can be strengthened or depleted, okay, depending on the new environment. So the rat so there are some mechanisms for creating these place fields as the rat is moving. And depending on the activity, this connection will increase or decrease a little bit. Now, the question I would be interested in is how actually the same network can memorize many different environments. But I'll come to that later. I don't know if I'm answering your question. We can talk more. Yes.
So, I mean, if you think that there is a region that is after another one, so you think, I mean, according to this, you think that the neuron that is coding for this position is firing before the next one.
Yes.
So if the two has some overlap, they fire together. So if they fire together, they should be closing the network, because
no.
Unless you have very long connection.
You have very long connection. So it depends on the region of the hippocampus. So in CA3, which is one specific region where there are a lot of connections, I mean not lot compared to n squared. So you have neurons, it's not lot compared to n squared. It's not. It's very sparse, but still it's large. there doesn't seem to be any kind of, short-range connection compared to long-range connection. It seems to be totally scattered. So there are long-range connections.
But why? I mean, why do you want this? Why do you want two neurons that are very, very far apart?
Well, very far apart. I mean, to some extent, I mean, it's a tiny region of the brain. Okay.
Yes.
But I understand your point. Yeah. But I mean, what does that mean? That there should be? Why do you want this thing here actually to look like? Sorry. I mean, it cannot hold for any for all environment.
No,
I mean,
no,
so I'm not sure I understand.
It's not that. I mean, this costs less in some sense because if the neurons are close, it's that in the other case you have to build the long axons and you have to maintain.
But I mean, this idea of cost. I mean,
okay.
if cost was so crucial, there would be no elephants, right? So I mean, there are some theories based on costs. Okay. So this is recorded, so people won't like that. I mean, but it's always very strange for me. I mean, I don't know. I don't really understand. I mean, why? So what is the cost? How do you measure the cost of building something with an axon which is, 100 micrometers long or which is 1 millimeter long? Is it so huge that the animal is not able to do that? I mean, I'm not sure if this is the right thing to be optimized. But I mean, what is known anatomically is that when you look at these things here, there doesn't seem to be any kind of short-range order, which is not always true. I mean, some cortical regions, you see very clearly some columns which are organized with near or neighbor or almost, I mean, actually, surely short-range couplings, and the different columns will interact together. So clearly there is some order, while here it doesn't seem to be anything.
Well, the cost could be not just the material to build the axons, but it could be a cost in speed at the end of the network.
Well, anyway, I mean, the speed in terms of propagation of these spikes along the thing, but these are short distances. You have to think that, I mean, so people always give the example of the giraffe. You have axons which are a few meters long, and they're still, from the head to the feet and so on. And still, I mean, it can propagate in a reasonable amount of time. So speed is not limiting here. There are anyway very short distance in the hippocampus. It's a tiny region. Okay, so this is the model. So now you ask, once this neural network is built, what is going to be the distribution of neural activity configuration? So in the case of the Lattice model, this is the zero-dimensional case, then we know that at low temperature, the model will generate configuration which are strongly magnetized along the sigma direction. So what is going to happen here? Okay, so we have to define the dynamics, and I will use the same dynamics as in the Hopfield model, which is physical dynamics. And that's just something which is actually inspired from neurobiology, but it's a simplification, obviously. So the idea again is that a neuron number I, will receive at some time t some inputs from the other neurons, whether they are active or not. This will be weighted by the synaptic coefficients, which is a function of the distance between the place field centers compared to some threshold. And if this quantity is let's say large and positive, then there is a higher probability to go from a state where sigma is equal to 0 to sigma equal 1 than to the other state, than to do the reverse transition, right? So it's some kind of finite temperature version of the Hopfield dynamics I showed you before, which was a zero temperature version. And we know that, so this thing obeys detail balance, which obviously is an oversimplification in the context of biology. But it's interesting because we have a stationary distribution for the activity of a population, which is given by these IZ models with coefficients, which depends on the distance between the place field centers in the physical space. Okay? So this theta here is just an effective field which maintains the activity to some level, because you have to see that all the coefficients here are essentially positive. If you take positive coefficients, positive interaction at short distances and zero at large distances, so the whole network will fire. So in order to maintain the activity to some reasonable level, then you need a negative field which is basically repressing the whole activity. Okay? So in fact, this model was introduced a long time ago in statistical physics in a very different framework, but this is the same model. In particular, in this paper, where people were interested in the liquid vapor transition, liquid gas transition, and they wanted to have let's say exactly solvable model for this transition. So in this paper from 1966, what people did, they consider some kind of, let's say, lattice gas model. So you have a lattice, 2-dimensional lattice, 3-dimensional, whatever, d-dimensional lattice, and you put particles on this lattice. So the lattice has n sides, and the number of particles is a fraction of n, which is constant during the dynamics. And you have very short distance repulsion. That is, each side of a lattice can be occupied by at most one particle. And there is weak positive interactions between neighboring sites up to some distance. Okay, so that means that particles have a tendency to cluster together on neighboring sites, and the total number of particles is fixed, which in our case amounts to find the value of theta, which maintains the global magnetization fixed. That's the same thing. Okay, so this model is obviously invariant under translation. That means that the interaction between two sides here is the same as the interaction between the two sides which are translated away from these two sides here. It's a function only on the distance between the sides. And so what is a phase diagram? At very high temperature, if I plot the density of particle as a function of space, this is the 1D case, but you could do it in 2D, it will be uniform over space, like in a paramagnetic phase. At very low temperature, you will get a cluster of particles which are occupied a very dense region. So you get a very dense region here. So that's a droplet of liquids, and which is surrounded by a very low density of particles. So it's a vapor surrounding the droplet of liquids. And there is the first order transition in between these two regimes with a coexistence here. So this model has been solved. So in order to make it exactly solvable, the idea is to have actually very weak couplings in the sense that J is scaling as 1 over the number of particles, and the distance here over which J goes to 0 is actually growing with the size of the environment, so that the number of interacting neighbors is of the order of n. So weak interaction and long range. Okay, that makes it some kind of mean fieldish, but still you get some trace of space here. The profile of density will depend on space. Of course, you can do the same thing in any dimension. You get the same kind of transition. So why does it correspond to what people are interested in neuroscience? If you think of this model along a 1D ring, so let's say one-dimensional space with periodic boundary condition, this is what is plotted here. If you are at low temperature, then you get this profile of density. So that means that, for instance, at a given time, if I look at my configuration of particles, so here each side can have a particle or no particle. In the neural context, each neuron can be active or silent, but it's the same thing. Then I will have a bunch of neurons which are very strongly active here. All my particles will be here. And if I look again at my model at another time, then maybe the bump will move and will be here. In fact, there is total invariance, I mean pure exact invariance on the translation, so the bump can diffuse freely along this ring. Okay? So we get really a one-dimensional attractor, and any kind of location of a bump, any position of a bump along this attractor is good. Okay, there is no distinction. So the shape of the bump is determined by the Hamiltonian, but then the position of the bump is totally random. So that people were interested in this kind of model in the context of neuroscience, because you see, we have a population of very noisy neurons, but still some kind of collective coordinate is emerging and is very robust. And this is the location of a bump here. So it's a way to encode in a population, in a robust way, a single effective coordinate. Of course, if you do that in 2D, there will be two coordinates. Depending on the dimension of the attractor, you will code for more than one coordinate. And the interesting thing is that the bump is persisting without any input. But if then you add a small input which actually drives the bump somewhere here, then the bump will move and will be attracted there. But you don't need the input to maintain the shape of the bump. Only weak in order to drive it somewhere. So it's a model which can encode coordinate, some information, and the information can change over time with very weak input. And still it's robust. So you can have 2 points of view, either at fixed time, as I said, you look at the population at any time and you see something, or if you have an electrode, you will put your electrode somewhere here and you measure the activity, and then if you plot the activity as a function of the location of this collective coordinate, the location of the bump, you will see something like that. And that corresponds exactly to a place field. As a function of a coordinate, the neuron will be very active, or it will be completely silent for a fixed neuron. And this is what people see in experiments in the hippocampus. So that's why this model was used in the hippocampus. Okay, so maybe I can, shall I stop here, and then I will go to the case of multiple attractors, which I think is interesting. Okay?
Okay, let's have 10 minutes.
Hafiz Model and how you can store multiple point attractors in your neural networks. And then I talk about Amaris model, which is also this Lebowitz-Penrose model, and how you can store one d-dimensional attractor in a network. So the natural question is, how can you actually combine two models and get the storage of multiple d-dimensional attractors in a neural network? But before I go to that, and this is the model by Samsonowicz and McNaughton, I would like to give actually some evidence, or I will present different slides of different experiments, which suggests that actually the hippocampus is not coding only for a specific map, but for different representation of a space, and not only a representation of a space, but the space plus something. And the something may be very important. It's called, in your biology, context. So actually, this is not really a well-defined word, but let me give you some examples. So here is an example of an experiment by Smith and Mizumori about 10 years ago. And what they did is the following thing. So they have a rat here, which is in a cross-shaped maze. And the rat is, at the beginning of the experiment, located at one of the extremities here, let's say one of the three extremities. So the north, the south, or the east, or the west extremity. And there is a reward, some food or water, on the east arm here. So what the rat has to do is to learn that it should go to the east arm. Okay? And the rat has 10 trials. After 10 trials, for the next 10 trials, the reward is moved from the east to the west arm. So the rat has to understand that it should go east 10 times and then should go west 10 times. Okay, so that's the thing. Now, if you do the experiments without any reward, so it's just an empty space, the rat will move. And what you find is that if you record in the hippocampus, you will see place cells. And if a rat moves 20 times, so that means that the rat moves, stops somewhere, and you put it back at one of the extremities and run that 20 times. So exactly the same experiment as the normal experiment, the full experiment, but without any reward. What you see is that cells will have place fields. And this is one particular place field here for one particular cell, which is recorded. And you see this cell will be very active here at the end of the east arm. And this is measured over many experiments. And each time you average the activity found over the first 10 trials and then over the next 10 trials. Obviously, there is no difference between the first 10 and the next 10 if there is no reward. Okay? And you find that the place field has not changed in between, which makes sense. Now, if you consider the full experiment when the reward is moved from the east to the west arm after 10 trials, and you do exactly the same thing, then the situation has changed a lot. So for instance, if you look at this thing here, you see that this particular cell will be active very close to the reward. It will code for the position of a reward. And after 10 trials, the place field is remapped to the other extremity here, to the other arm. So that means that the cell is not coding only for the position, it's coding for position in a particular context. And you can see that also here, these cells will have different place fields, depending on whether you measure its average activity among across the first 10 or the next 10 trials. Okay? So we see that it's getting more complex than simply coding for position. Now another experiment where it's getting even more complex, this one. So here a rat is located in this circular arena, and this arena is actually rotating. So there is a rotating disk here. And there are two zones, the blue and the red zones. One is moving and rotating at the constant angular velocity, and the other one is fixed in the room environment. On the two zones, the rats can get electric shocks. That means there are zones that the rat want to avoid. Okay? So the rat has to learn to avoid this zone, but the difficulty is one is moving. Okay? Now, if you recall the activity of different place cells in the hippocampus, you find these kind of things. You find place cells whose place field is actually fixed in the room environment. Okay? So this is coding for positions in the room environment. So for instance, this one, which is called a room-related place cells. So what you see is the activity Okay, so you see different angles of the blue zone with respect to the red zone. So the red zone is fixed, it doesn't move. The blue zone is moving. So at different angles, average angles, what you can do is measure the activity of these particular cells, and the black trajectory is the trajectory of the rat, and the red dots correspond to the position of the rat where this particular recorded cell was active. So you see the cell is always active here, opposite to the red zone, so somewhere here. And this is independent of the position of the blue zone. So it's coding for position in the room environment. But you see cells which do the opposite. They seem to be locked to the rotating frame, and they code for position which have a fixed angle relative to the blue zone. Okay, so that means the rat is actually have a representation. They have two kinds of representation. There are cells which code for position. The activity will tell the rat immediately where the position where it is compared to the red zone, and the other ones compared to the blue zone which is rotating. Both are important, obviously. Now the question is what kind of representation is activated at any time in the brain, in the hippocampus, and it seems it depends on the relative locations of the two zones with respect to the position of the animal. So the animal is somewhere, and it has two distances with the two zones, okay? And the two distances will change because the animal is moving and because one disk is rotating. So they change over time. So here you see the two distances with the blue and the red zone as a function of time in some experiments. And what people have done in these experiments here, they have measured, I don't want to get into details, but they have measured they have defined some kind of measurement of recruitment of these room-related place cells and arena-related place cells. So what they do, as a function of time, at any time in a time being, you can say, let's look at the cells which are activated, and what is the fraction of the cells which are activated which correspond to this one or to this one. And you measure some kind of difference between the two. Okay, I don't want to get into details, but you understand the idea. You want to understand whether the mental representation of space in the hippocampus at time t is based on this population or this population. And what you see, actually, this thing is changing over time, and it's related to the distance. I mean, essentially, the rat is activating the population which correspond to the closest zone. So if the rat is closer to the blue zone, it's better actually to have an accurate representation of a relative distance to the blue zone, so it's better to activate this population. Otherwise, you activate this one. Okay? So the idea there is that there are different mental representations of the same environment, because there is a single environment. It depends on what you call environment here, but I mean of this particular environment. And you can have different mental representations. Some are more useful depending on your situation. Excuse me, on your situation, your position in this particular environment. So this is interesting because it gives the idea that there are different ways of coding for position depending on the context, on what you want to do, and depending on the region you want to avoid. So all these representations are useful. So what is the best one? And they should coexist in the hippocampal network, and the rat should be able to evoke one representation rather than another, depending on stimuli and depending on inputs. Okay, so I want to show one experiment where this is actually measured in details and at a very high speed. So this is a teleportation experiment, which was done in the Mother and Mother group. So the Mother and Mother, they got the Nobel Prize in 2014, together with O'Keefe, for the discovery of grid cells. I will mention at the end of the talk today. So they are not place cells, it's something different, which is very much related to. Okay, so what they did in this experiment is some kind of teleportation of rats. So what does that mean? So again, you have an experiment where a few tenths of place cells are recorded in the hippocampus. And there are two different regimes in this experiment. The first one where there are two boxes which are connected by a corridor. And the two boxes are absolutely identical in shape. The only difference is that there are dim lights on the top of the roof of this box here, and there are dim lights on the side of the roof here. So the light conditions are slightly different. So the rats are not very visual animals. They can see, but if you put dim lights and they don't see so well, I mean, it's a slight change of inputs. to give you an idea, this is a 60 centimeter square box, and the length of the corridor is 2 meters. So my drawing is not at the right scale. So they are far away from each other. So they are so far away from each other that the rats really understand there are two different environments, so they are very similar in terms of shape. So for weeks, the rat is trained, and it can go from one box to the other and so on. Okay? So now, if you record the activity of cells in this condition, what you see is that the same place cell, so one particular place cell, will have different place fields in the two environments, so in the two boxes. So for instance, this cell number 1, which is recorded, will be very strongly activated when the rat is next to the corner here in box A, and will be activated here in the top part of the box B. Okay? So it codes for two different positions. It's not the same position in box A and in box B. In fact, if the corridor is too short, there will be the same two positions. Now, a very nice experiment where people see what is the size here of a corridor you should put in order to ensure that there is a remapping and they code for different positions. Okay? So that is called remapping, and in the same cells code for two different positions. Okay, so that's the training phase. Now, in the test phase, there is a single box with some light switch, which allows the operator to change the light condition immediately, abruptly. So the rat is some way teleported to the other environment immediately. So, okay, so now the question is, how do we understand what kind of... So it's a way to evoke different mental representation, right? Different spatial representation, and to study the dynamics. So this is related to the experiment I was mentioning before, but in a very controlled way. So one thing we can see is how actually these representations are changing over time. So here I'm coming more to the inference part, because this is should talk about inference and learning. So so let's do a little bit of machine learning to understand, to decode from the activity which is measured, what is the representation. So this is very simple thing I'm going to explain now. So we again use the kind of techniques I mentioned in the previous weeks. So what we have here is, at any in the time being, we have the activity of few tens of cells. And we like to know from the activity whether the rat has a mental representation which corresponds to box A or to box B. Okay? And in particular, it would be very interesting to see whether this mental representation agrees or not with the light, because this is not obvious. Okay? That's the point we'd like to understand. So a way to do that is to do something simple. Since the positions of the place fields are not the same in the two boxes, and we have many place cells, we have maybe 30 of them, then the adjacency matrix in the two boxes will be different. So if we compare the activity of neurons to the adjacency matrices in the two situations, we should see whether actually the neurons we are activated are close to each other on one network, and it seems reasonable, or they are far away on the other networks, and it's not reasonable. It's not a state of activity you would expect, right? So it's a way to decode for the representation based only on the activity. So if we want to be a little bit more precise than that, we can have here, if we have a configuration of the activity, we can draw two models for the configuration of activity. One model when the rat is in box A, another one when the rat is in box B, and we can draw these models from the training phase. And then in the test phase, when we have S at time t, we can compute, for instance, the ratio of the probabilities of this activity configuration within the two models. And the log of this ratio will be either positive or negative. It's positive, that means the activity is compatible with model A, with the rat being in box B. And if it's negative, it's compatible with the other one. Okay? So it's a very simple way of decoding the activity. So again, this is the neural space. You have neurons which may be activated at different places in the two environments, A and B. And we built a model which is relies very strongly on the adjacency matrix. And so we built a model where we need some effective interaction between the neurons. So the simplest one is an Ising model, where you have fields which code for, let's say, the mean firing rate, and effective interactions which tell you whether these two neurons can fire or not together in this particular environment. So we get two matrices here, one for environment A and one for environment B. Okay? And then we compute this thing here as a function of time. So let me show you what it gives. Is it clear? I mean, for a procedure, okay. Using the techniques, for instance, I mentioned the pseudo likelihood inference algorithm last time, and this kind of thing. So this is what you get for delta L. So remember delta L, and maybe I should write it here. Delta L is the log ratio. So it's the probability for the activity to be in A, generated from A, over the activity to be generated from B. This is the same formula as here because I'm assuming that the prior probabilities over A and B are 1/2 each, so it doesn't matter. Okay? So in the training session, when the rat is in A, then delta L should be strong and positive, and when it's in B, it should be strong and negative. And this is what you get here. So you train the models from a part of your recordings in one session, and then you test on the other part to avoid overfitting. And this is what you get. So you see delta L is positive. There are a few excursions to negative values here, but it's mostly positive in A and mostly negative in B. And the two histograms are more or less separated. There is a small region where they overlap, close to 0. These are time beings in which you cannot call whether, you cannot say whether a rat is in A or B. Two-week signal. Typically, this is when there are very few neurons which are active, maybe 0 or 1. It's very hard to say anything. Is it clear? Is it clear? So we have an algorithm which tells us from an activity configuration in timing whether the mental representation is A or B. And we are not exploiting any information about the position of a rat. It's only based on the typical correlation in the population. So when you apply these kind of things to the experimental data, this is what you get. So this is as a function of time. So this is theta cycle. So this is a unit of, I mentioned this theta rhythm before. This is 125 milliseconds essentially. Okay, so you have to divide by 8 to get the number of seconds. Okay, so here you have a vertical red bar, which corresponds to the time at which the light was switched from one box to another one. Okay, from one light condition to another one. So you see, before here we have delta L negative. That means that the light position was probably corresponding to the one of box B. And then it switched to A, and we see something which is interesting. At long time, it goes to positive values, but there are clearly some kind of oscillations here. Okay. So that means that for a few seconds, actually, as you see, we have maybe 20 cycles, maybe 3 seconds, or 40 cycles, 5 seconds, depending on the experiment. There are oscillations, that the representation is changing. And then it will stabilize to the right value, which is the one in agreement with the light position. One thing you can see actually is that if you look at the distribution of the time, so you see positive values, negative values, and so on. So it's a little bit difficult to do, but you can estimate the duration of these things here. And this seems to be exponentially distributed, as you would expect for a two-level system, right? Okay, so one question is how can we understand that, and how could we model, as I mentioned in the introduction, how can we have a model where we have different attractors, one for one environment, the other one for the other environments, and how can we understand transition from that? So there are not spontaneous transition here, in the sense that they depend on some change in the input, the visual inputs. But then the visual input is stable, so something is going on here. There are some spontaneous transition here. Okay? So why is it so? So first of all, how do we have a model where we have different attractors? So this is the Samsonovich-McNaughton model, which is a mixture of the Hopfield and the Amari model. So one thing actually I wanted to mention before I'm going to that is that when we do the inference of the effective GIJ from the data, we can look at how the GIJ depends on the distance between the place field centers, whether, just empirically to see whether it matches with the Lebowitz-Penrose model. In fact, it does. Here, so actually it's very much noisy. But you see, if you plot Jij, so for each pair of neuron I and J, and I have 34 times 33 over 2 pairs, you can plot the value of Jij and the distance between the place field centers, which is what not used for the inference. And you see clearly this is a sliding average. It's positive at short distances. It becomes more or less independent of distance and slightly negative at large distances. So it's compatible with having a model where you get this attraction at short distance and repulsion at long distance. But now if you want to memorize more than one environment, that should be true in any environment. So for the same pair of neurons I and J, the distance here will depend on which environment I'm considering. So there should be a Jij contribution to Jij which depends on the distance in environment 1, and this value here will be different in environment 2. So we need a Jij which is compatible with the two distances at the same time. So, and the idea that was proposed in particular by Samson McNaughton is the following. So let's do exactly as the Hafiz model. You can build an adjacency matrix in one environment. You do that in the other environment, and you just sum them. So just have an additive model. When you pile on top of each other all these matrices. Okay? So it's a kind of random matrix model. So for instance, if I have a 1D environment with periodic boundary condition, this is my space. Then there will be some place fields. So this is, for instance, neuron number 1. This is neuron number 1. It will have a place field covering this part here, right? Now on neuron number 2, and I can always order my neurons to do that, we have a place field here. Neuron number 3 will be here, okay? And so on. So in this particular environment, the Jij matrix will be some kind of band diagonal matrix here, and the width of the band will depend on how much these different place fields overlap. This is environment 1. Now what about environment 2? Now the same neurons will have different place fields, and in the simplest model you can think of, you can draw a random permutation of the assignment between the neurons sets and the set of place fields, okay? Which correspond to having a new matrix, J2, which is just some kind of permutation of J1. So you can do a random permutation of the lines of the columns of J1, and you get a new matrix, which corresponds to a new assignment between the neurons and the place field. Same number of place fields, same number of neurons, but they are connecting in a different way, because they are scattered in a random way. So that would be for one permutation, and then you can think of a third environment, exactly the same thing, where you have a new random permutation. And now add all of them together and ask what is going on with this model. This is the idea of the model. Okay? So this model has a nice phase diagram. So this is a phase diagram of a Hafiz model I briefly recalled before, informally. At 0 temperature, you have this phase transition at alpha equal to 0.14. Alpha is the ratio between the number of patterns, number of fixed point configuration, and the size of the network. Below this critical value, you get local minima of the energy, which are close to the memorized patterns. And above, this is the spin glass phase, and there is no correlation. So in this model, you get something similar, except that now, so there are two differences. The main difference is that this is temperature, as in the Hafiz model, so this is the same axis. But here, now the axis is not the number of fixed points over n. This is the number of environments over n. Okay, so how many matrices you sum up here over the number of neurons. And at low temperature, you see one phase where you could have a bump of activity in one environment, and it would be essentially random in the other ones. And above this critical value of alpha, it will be spin glass phase, so no correlation, no bump of anything. And which environment has a bump depends on the initial condition. Is it okay? So it's a way to memorize different environments in the sense that if I look at a typical configuration of my system in this alpha T regime, in this region here, then the number of the neurons which are active have place fields which are close to each other in one of the environments. So they code for a specific position in this particular environment. Is it okay? So one thing which is interesting actually, and which is not well understood, is that the contrary to this Hafiz model, because here I erased because I wanted to make the thing simpler, but you can still see a little bit of line here. I mean, the low temperature regime here is actually complicated. There are regions where the local minima are not global minima and so on. So in fact, the basins of attractions are not very large in the whole field model. If you go to large alpha, it seems here actually they are much larger. That means you always essentially crystallize and condense it into one of the environments, and not in a glassy
So
thing.
this diagram is because you have an underlying space.
Yes.
Which dimension is
This is d equal 1. So all
okay.
I didn't put any numbers because
Okay.
here you get the universal numbers, but here there are many more parameters. You have to fix the average activity. You have to fix the range of the connections. So it's not a
Is it
single.
the same equal.
Yeah, it doesn't change anything. Any d. It's a mean fieldish version, right? It does not depend on d.
Okay.
Infinite
So
range.
the finite d doesn't enter.
No, no. Okay, so let me show you one simulation of the model so that you better understand what is going on. So this is a case where you have 3 matrices. So that means there are, so there is another one. So there are 2 random permutations, and the number of neurons I think is 1,000 here. And this is a 2D, or maybe it's 900. I mean 30 by 30. I don't remember. Yeah, 90 by 90. Well, 90 by 90. So this is. Yeah. Okay. 90 by 90. And so in 2D, and so you understand how the model is built. I explained. So you see a simulation. So it's just Monte Carlo simulation, very simple Glauber dynamics. So you see as a function of time. So what do you see? Obviously, at any time here, there is one single configuration of the network. So you get the value of a neuron sigma 1 up to the value of a neuron. Up to the value of a neuron 8,100. Okay. Now the question is, how do you represent this activity configuration? And there are 3 ways of doing that. So either you represent it in the first environment, the second one, and the third one. And here the idea of the representation is put a dot of the corresponding color. So we have 3 colors, one for each environment, at the center of the place field of the neurons which are active at this particular time. So here we start with an initial configuration where we have the very nice artificial bump in environment 1, and it's scattered all over the place since the permutations are random in the other environment. Okay? And how does that evolve? According to the global dynamics with the Hamiltonian dimension. Well, you see you get a noisy bump in environment 1. Actually, it will diffuse a little bit. So we don't have perfect translation invariance between, I mean, the Hamiltonian in environment 1 is perfectly invariant on the translation, but the other ones are random. So there will be some kind of rug landscape. But still, it can diffuse a little bit. And at some point, you will see, so these are the different contributions to the energy. You will see a transition to the blue environment, where the bump appears in environment blue and then it disappeared in the red one. Or there is some kind of denser thing here, but I mean it's scattered. Okay, and then there are different transitions. If you wait long enough, it will be bumpy in the green environment. So you see spontaneous transition, that in the activity becomes coherent with one of the 3 matrices.
And there seems also to be a sort of oscillation. Is related to the oscillation. There seemed to be a moment where there was a bump reforming in the red.
Yeah, so you can have states which are actually not really totally bumpy in one environment. Okay, so maybe I can run it again. So can we go directly to the end? I don't know if we can drive it. No. Yeah, so I mean, in this region here,
yes.
I mean, you see some region where actually we have some kind of half state, mixed state, with some kind of 2 small bumps. So that's an interesting thing because it tells us something about how you do a transition from one environment to another one. And I'll come to that. But there are different scenarios for that. Depending on temperature and alpha, depending on where you are in the phase diagram, one possible scenario is just evaporation. So you go from one environment to another environment through the paramagnetic phase. No bump, and then it will condensate back in one of the in another environment. But there are also some kind of wormholes. So I'm a little bit overstating that, in the sense that specific region in space where actually it's easier to go from one environment to the other one, simply because locally the matrices are similar to each other. What do I mean by that? Suppose the bump is moving, and then you will have a bunch of neurons, let's say neuron I, J, K, L, and so on, which are activated at some point. So that means that they are connected to each other in environment 1. But maybe by chance, it turns out that they have also positive couplings that are connected in environment 2. This is possible, just by chance, right? And that happens if you have very big matrices. You can compute that the typical lengths of that you would get just by chance. Then in that case, the bump is, you get a mixed state because it's already it's a little bit bumpy also in the other environment. And these are specific places in space where it's easier to nucleate the bump in the other environment. And you can see that.
Sorry, do you know what happens if there are two environments that are, well, not completely different, that are similar in some way? I mean, will there be similarities between their representations?
Yeah, so this is related to the fact I was mentioning about the length of the corridor. So people have done this. I mean, they looked at, they did experiments where you have a room, and one of the wall is actually a moving wall. So it's a piston that you can move away, okay? So the rat is moving, and you have one particular place cell, and it has some place field here. So what you do is that you can move this thing here away, and see what happens. So there is some kind of elastic deformation here, so the thing will just grow a little bit. It basically occupies some kind of almost constant fraction of the space here, up to some deformation threshold, and then you get complete remapping. So this thing will disappear, and then in this larger thing here, larger wall, then maybe it will be somewhere here. So there is some kind of adaptation, and then some discontinuous thing. So this is again the idea of there are different attractors which exist, which can be a little bit distorted, and then you move to another attractor for the representation. Is it okay for that? Okay. So one question is, okay, this is nice. We can have spontaneous transition, but it doesn't tell us anything about what happens when you change the input. Okay, you can move from one attractor to another one depending on the different inputs. So people have been very much interested in that in neuroscience, and I want to show you two different experiments where people change the inputs. So one experiment, which is actually a whole field of virtual reality, which was initiated a long time ago, is the idea is that if you want to change, for instance, so when we move, when the rat is moving, that's the same thing, we get different streams of inputs, so visual inputs, and I get, for instance, vestibular information, acceleration of the head. I get also integration of my motion of the legs and so on. And all these inputs should be coherent, okay, because I'm doing some real motion. So it's very hard to distinguish between the contribution of all inputs when they are coherent. So what people do, they will build artificial situation where there is some conflict between the inputs, and we see what kind of input is winning. And that's a way to distinguish the different strengths of the inputs. So a nice way to do that is virtual reality. So this is an experiment which was published a few years ago. So how does that work? Typical setting is this one. You have a rat. The head of a rat is actually fixed. It's maintained. And the rat is actually moving on the ball. So it's moving its legs. And you have a screen, which is a very wide screen, which is projecting a movie corresponding to the motion of a rat. Okay? So in principle, you can integrate the motion of the ball to know where the rat is in the maze or in a virtual environment, and you should project to the rat exactly what he should see at this position. So there is no conflict between visual and past integration inputs. So there is no vestibular input here. The head is fixed. That's nice. And when you do that, you see place cells. So the environment here is a 1D maze. So it's a corridor. The rat is moving around corridor, and the walls are circulating as the rat is moving. So you see, for instance, this cell here will be activated at one part of the environment, which is at the beginning. Another one will be activated at the end. So you see place cells as in reality. Now what you can do is actually decouple the speed of a movie with the speed of a ball. You can make the movie go faster or slower. Okay? And now you can see where are the place fields. So some cells, for instance, are not happy with that, and they will completely lose place field in one situation. For instance, when the ball is so passive moved, that means that, for instance, the motion. So even if the ball is not rotating, the movie is going fast. So this place cell will lose its place field. It's not a place cell anymore. And you can do things where you decouple, so one of the two is going half the speed of the other. And you see in some cases actually the place field change. They can be shifted a little bit. And for instance, in a passive move, this the situation, this place cell actually has shifted a lot. So it means that some place cells typically get information either from the visual input, either from the path integration of the integration of the motion of the legs, and they determine their place field principally, mainly based on this information. And there are subpopulations of place cells which integrate different kind of inputs. Or there are also mixed place cells which integrate both. Okay, so that's a way to measure the different strengths of the input. Another very nice experiment. So there is a bunch of experiments in the group. I didn't mention the paper. That's bad. So there is a series of experiments on bats in the group by Ulanovsky at the Weizmann Institute. So bats are very interesting animals because they fly. So you can measure the third dimension and see what happens in the third dimension. So they did a lot of experiments. In particular, they found also place cells in bats, which are very similar in the z direction compared to the xy. So it's a ball. And as the bat is flying, it will be, this particular cell will be activated when the bat is crossing this particular ball. And there are very nice experiments either in control rooms, which are just small rooms, maybe a few meters or whatever, and also in free motion on very long distances. So you can see place fields on distances of a few hundred of meters, which are very amazing. They are building tunnels actually of a few hundreds of meters long, so you can see all these things. So here they look at one species of bats which had the capacity of having a very good sight. So usually we think of bats as animals which are not able to see, but that's not true. Some species actually have very good view and very good sight. So they can use visual inputs in order to move without absolutely any difficulty. And of course, they have also echolocation. So they can use also sounds in order to know where they are in space. So how do you put conflict between the two things? So one possibility is to remove light, so put in the dark, so visual inputs are not present anymore. Or you can perturbate the echolocation by emitting sounds at the same frequency, which basically remove any possibility to orientate by echolocation. So what they do exactly the same thing. So exactly the same thing as here. They look at some particular cells and they see to which position they correspond, so where are the place fields, depending on the sensory modality which is usable. And you see, for instance, here, light, where you have vision, dark here, and light again. But you see this place cell, for instance. So obviously this is in 3D. So here you see two projections. You have the XY plane and you have the Z here. So this is projected on X and Z. So this is X, Z, and Y. That's projected on XZ plane here and XY. So you see this place cell, we have a place field here, and you have the same at the end of the experiment. And when you use only echolocation without visual stimulus, this place cell is not active. Another one will be mostly active based on echolocation, but not on visual stimulus. So again, this idea that there are different place cells, and they use different streams of information to build their place fields and to be activated. Okay? So, yeah. Okay, so in the experiments I mentioned here, so what are the inputs? So one input is the visual input, because the light conditions are changing. Another one is the animal is moving. So there is clearly a conflict between the two, because as the animal is moving, it knows it has done so. As the light is changing abruptly, the motion of the legs is small between right before and right after the change of light, but the change of visual inputs is huge. So there is a conflict between the two. And this is why we see this oscillation here in the representation, simply because it's expressing the conflict. So we can understand that, and showing this briefly, because I would like to show a bit more of experiments about attractors at the end. So essentially, when we have two attractors, we have one continuous attractor, which corresponds to having an activity concentrating as a bump in environment A and scattered all over the place in B, or the opposite attractor. So these are not point attractors. It can move anywhere in the space here. And in between, we can have this kind of mixed states we were mentioning before. And So if we have this two-level representation, which is obviously an oversimplification, but essentially the idea is that we can change the relative height of the two wells here, depending on the kind of inputs which are used in order to materialize these bumps. So one way to think about that is the following. Okay, so there should be some inputs projecting from the cells coming from the visual stimulus. And there should be some inputs coming from the path integration of the motion. So it's a very complicated story. I will just say a few words after that, how this path integration is done. But let's assume, just from a theoretical point of view, that the cells, the neurons, the sigma I, receive some fields, the hi, which depends on the visual inputs and on this path integration of the motion. So some cells maybe will be strongly connected to the visual information, other one will be strongly connected to the path integration, and it can be a little bit random and so on. Now, if both, the fact is the following, is that when the animal is in some position in environment A, then some cells will be activated and they code for this position in environment A. The same position in environment B is coded by other cells. So for a given visual stimulus, we'll have some connections, some inputs coming on these cells coding for position X in A, on the other cell at the same position in environment B. Okay? So for the same position, they will not project onto the same cells. They will project on the cells which code for this position in this particular environment. So now when you have a conflict between two things, that means, for instance, the path integration, as we change abruptly the light, wants to be continuous and is projecting onto the cells coding for the new position X prime right after the light switch in environment A, which was the one we had before because the light condition was in A, then this thing has a tendency to move the bump in environment A, while the visual stimulus is actually pointing to the same position, the physical one, in environment B. So there are two populations of cells which are tried to be activated together. But at the same time, there is a cohesion between the population due to the network recurrent connection, which said that there should be a single bump. So you want to activate two different subpopulations, but there should be a single population activated. So the conflicts come from that. So now, let me show you a simulation. So you see, for instance, here, this is the light switch, the red thing. So before the light switch, we have a single bump in environment A. And then due to this conflict, you see that the bump is jumping from A to B in a random way until it will stabilize in environment B. So why can it stabilize? I mean, in principle, the conflict is there. Okay, the path integration is still integrating from the past environment. Okay, so that's an interesting question, which is related to what people call path integration resetting. Is that when you have different modalities, sensory modalities, there are some which are actually more reliable than others. So visual stimulus, I mean, we are very visual animals, so we really trust very much visual information. We are not very strongly olfactory animals, for instance, so we trust less. If we have only olfactive interaction, we will use it because that's the only thing we can do. Otherwise, we will prefer use visual information. That's the same thing for path integration. Visual information at some point is better than path integration, which is very not precise. Okay, so there is some kind of adequation at some point between the path integration and the visual stimulus. Okay, so before I move to show, I just want to show that actually this kind of picture is coherent with the data, and to show you that. Because we can use, if you remember, I told you from the place cell activity, you can decode the position of the animal. But in order to do that, you need to specify the set of rate maps. So you need a correspondence between the activity of this particular cell and the position in space. And it won't be the same in environment A and environment B. So what you can do is to decode position, for instance. This is the x, y as a function of time, using the place field, the rate maps of environment A. So this is A before the light switch. This is B after the light switch. So if you do that, you see a nice agreement between the inferred position and the true position. And if you do that exactly after the light switch, this is not a nice agreement. Okay? And in fact, this is consistent with the fact that there are many oscillations here where the mental representation is not the one corresponding to the lights, but it's an internal representation, which actually may be at some times equal to the one before the light switch. So there is a disagreement with the mental representation and the external condition. So now if you use the map which is decoded by the Ising model, this is our proxy for the right representation, you see that the agreement is very good. So that means something of, so if I want to say that, to phrase that in a very informal way, there is an information which has to be coded at any time, which is position, but there are two languages to code it. Either you will code it in the map of environment A or in environment B. Now it seems that the languages is switching a lot at very fast frequency, okay? It's changing a lot, but the information is always precise at any time. So two different ways of representing exactly the same thing. And position is very finely encoded at any time. But the way it's encoded from a neural population point of view is completely different. It's changing a lot. Is it clear? So it's very important to have different representation for the same object. Because suppose, for instance, now, for some reason, when the light is on the top, on the roof, then the animal has some reward. And when it's on the side, it never gets anything. So coding for position is not sufficient. You need to know in which context you get this position, because then it can be associated to some particular motor task, some change of motion that the rat has to do. So the representation is very important, not only the position. Okay, so let me, maybe one thing I would like, and then I will show some other experiments, and then I will stop. Yeah, actually there is some kind of evidence for this kind of mixed state when you have two bumps, but okay. So I think I should stop, and I have 4 more slides which are purely experimental, just to give a bit more evidence for that. So here everything was based on attractors, and I have used the representation of space to do that. So, but okay, so I would like to give one more evidence for the evidence of for attractors in the representation of space, which are based on grid cells, I already mentioned, and then I move also to auditory cell assemblies in a couple of slides. So one question here was, I mentioned this mysterious path integration mechanism, which was able actually to give inputs to the cells. And we know it exists. I mean, clearly, there is path integration here. There are cells which actually whose activity is based only on the integration of the motion of the legs here. So how is it done? So that's a question that people have been interested in for a long time after the discovery of place cells. And there was a major progress in 2005 by the Moses and Moses, in this paper. Oh my God, you can't read anything, 2005. So the idea was the following. Here is the hippocampus in the rat brain. So you can see the shape of the hippocampus, where you find place cells. Now, anatomically, if you look at which part of the brain is actually projecting, is actually sending information onto the hippocampus, you find many different regions, but one is called the medial entorhinal cortex, which is this part here. So the idea that the Moses had was to say, okay, so let's put electrodes in this region and see what is going on. So they did that, and this is what they got. So these are 3 different cells which are recorded at different depths in this medial entorhinal cortex. And what you see here is a representation of the activity of this particular cell, here the second cell, here the third cell. So this is the environment of a rat, which is a square environment. And the black line is the trajectory over minutes. The rat is moving a lot in this environment. It's an empty environment. Each time this particular cell, which is recorded by the electrode, is active, you put a red dot. So first of all, this is not a place cell, because in a place cell you would get a patch here very much activated, and that's it. So you see this is activated all over the place, but with preferences at some position, which actually correspond to the nodes of a triangular lattice. I mean, approximately. If you go to deeper regions in this medial entorhinal cortex, you see exactly the same kind of picture, but the mesh of a lattice is increasing. So people report experimentally that there are 5 different mesh sizes. It's not a continuous process. There seems to be some kind of discrete set of sizes which are more or less in geometrical progression with a ratio which is about, you see, 1.4. So it goes to higher and higher sizes when you go deeper. So this was a major discovery, and since that actually these grid cells are very important to stabilize the activity of place cells. And they give you information about position, to the place cells, and they seem to be very important for place cells. So that was believed in 2005 in the next years, and then the situation is more complicated now. It's not so obvious. In particular, if you look at the development of rats, you see that the place cells arise before grid cells. So clearly, place cells can be activated and can be found before grid cells. So they do not need grid cells to form, but maybe they need grid cells to get reliable inputs at later stage of maturation of the animal. Anyway, so how do we build model for that? We had model for place cells. We can build model for grid cells. So it's easy to think about. You can build a model, and that was done by some people. So in the model we have here of place cells, I don't want to redo everything, but you see, what was the ingredient? We had interactions which depends on position here, and we had some kind of inhibition here, which was basically repressing everything. So it's a global inhibition here. But if you have an inhibition which depends on distance, it's not global, but you let's say short-range attractions between particles, if you want, and then a little bit longer range repulsion, and then you stop. You don't put it to infinite distances, right? Then that's fine. You will get a bump here, and then it's not interacting with another bump, which you would create here, and you'll get a triangular lattice because that's a more stable thing. So it's a way to build grid cells, and you get the same kind of continuous attractors in d dimensions, and that's the classical model people have right now about these grid cells. So there is some experimental evidence for the fact that this is an attractor. So I don't want, this is extracted from this paper. Oh, I didn't mention the paper. So it's a paper by Yoon. If you want, Yoon, Fitter. That's the first author, that's the last author, and there are authors in between, but I'm ashamed I don't remember. In 2013. So what they do the same thing. They record a grid cell, and they at different times, and over long periods. And then you see how this grid here is moving. So what you see is that if you record for some time, maybe 10 minutes, 20 minutes, you get this picture here. And if you do the same thing a long time after that, so it can be, I don't remember exactly, but few days, I think, which is not trivial at all because you have to be sure you pick up the same cell. You see the same kind of grid, but it's shifted. In fact, in a continuous attractor, along the attractor, you would expect the bump to move, right, to diffuse. So it's normal, it shifts. It just randomly drifts away. And if you do that for another cell, which is next to it, you see the same kind of thing. It's drifted, okay? But now if you measure the difference of drift between the two cells, then you see it's very weak. And this is what is represented here. They call it a phase, so that's the difference of vectors of translation. The difference of phase is actually much more, the difference of relative phases is actually much smaller than the one of single cell translation. So we have the idea that all these things are actually moving, drifting on the continuous attractor, but in a concerted way. They're locked to each other, as they should be on an attractor. So it's an indirect evidence for the notion of attractors. And then I will show two more slides in a completely different context, which is more related to Hopfield model. These are cell assemblies in the auditory cortex, which I wanted to mention. So it's a paper, I'm sorry, and it's missing here again. That's bad. So it's a paper by somebody called Batelier, who is actually at the École Normale. And I think I don't remember the year, maybe 2010, something like that. 12? Oh, sorry, it's written somewhere? Oh, yeah, okay. Very good, thank you. Okay, so you can read it. I was not able to read it. Yes. So it's 2012. So what they did, so now we are moving away from the representation of space. Now we're interested in the representation of sounds. So they use, so I want to mention that for two reasons. First, it's a very beautiful experiment, and the second reason is based on a completely different experimental techniques. So instead of putting electrodes in the brains and measuring the activity with electrophysiological devices, they do optical recordings. So the idea there is to have neurons which are engineered. So there is some genetic engineering of neurons. So they are modified neurons, in the sense that when they become active, they will be fluorescent. So the idea is that you insert inside the genomic material of the neurons through some viral vectors, you insert some proteins which are sensitive to calcium and becomes fluorescent when calcium level is high. There are probes for calcium. Now calcium level becomes very high when the neuron is active. So you see fluorescence. So how do you image that? So it turns out that the auditory cortex in mouse is very close to the skull, to the external part of the brain. So what they do is that they try to make the skull next to the cortex as thin as possible without breaking it, so that it becomes essentially transparent. So you can image the superficial layers of the cortex right under this almost hole, I mean close to hole region. So this is essentially what they get. Okay, so now, you see you can image the activity of a few neurons, and this neuron will be active or not depending on the sound which is presented to the animal. Okay, so now that's interesting because I just want to show you this experiment and then I'll stop. So here you see different cells which are recorded for different trials. So they record about 70 cells, okay, and they will record the activity of these cells by imaging like that when some sound is presented to the animal, sound A. Could be a pure frequency, it could be a mixture, and so on. So the cell will be active with some frequency. Some of them will be silent, other one will be much active, and so on. And you repeat this, and you measure that for some time. You stop, and you do it again. And you see that these are the trials, okay, and these are the cells. So what you see is that actually there is a large variability between trials for the same sound. So it's not a deterministic response. It's very noisy. Okay. Some cells are very much activated, other ones are very often silent, and so on. But it fluctuates from trial to trial. So you can see some kind of regularity, despite the fact it's noisy. Okay. Now you can measure some correlation between the activity corresponding to the same sound on two different trials, or two different trials corresponding to two different sounds. And you see that the correlation is much stronger between the trials corresponding to the same sound than between trials corresponding to different sounds. So it's very noisy, but there is some average signal there, okay? Okay, so now what happens, suppose you have some template, which is your, let's say, average response for this particular sound, and you have your average response for this particular sound, and the question they ask is what happens when you do something like that? You move from one environment to another one in a continuous way. So how can you do that with sounds? You do a mixture of two frequencies, sounds A and B, but with some amplitudes which varies continuously for being pure A to pure B. What is going to be the response? So and this is what you see here. So we can look at, for instance, at this thing here. So here you see a mixture between. So you see, for instance, what is going on when you have a sound at this frequency. So it's a pure frequency. And here it's another pure frequency. And the width here is the amplitude of a sound. So here it's a strong sound, and here it's essentially zero. That means the response, the activity of the neurons is very weak. So each box here is a cell number of the number of trials as before. Okay? And you see that if you change the amplitude, if you compare two trials here at different amplitudes, if the amplitude is not too weak, then essentially you get the same response. And if it becomes too weak, you don't get anything anymore. Same thing for a pure frequency here. Okay, as the amplitude becomes weaker, then you get nothing at some point. Now what you can do is actually do a mixture, and so that the total amplitude is changing here in a continuous way between the sounds, and then you can measure the response and compare to the two pure responses. And what you see is not at all something linear. It's something highly discontinuous between a response, an activity which is very similar to this one or very similar to that one, and nothing in between. Which is something totally non-obvious, okay? So it means that there is some kind of population activity here, which is typical of the first sound, typical of the second sound. And when you excite with inputs, then the activity, the population will decide whether it goes to the first attractor or to the second one. And then at some point you change the amplitude, at some point you move to the other one. But there is nothing in between. It's not a linear combination of the two. So that's a strong evidence of the existence of attractors here. They are not d-dimensional attractors, they are fixed points here, noisy fixed points. Okay? which I find very nice because it has nothing to do with the representation of space. It's a completely different thing. So it's nice, I think, that these ideas which were put forward in the 80s by Hoffman and other people, about attractors, which for a long time have been completely, theoretical thinking or whatever, now they are supported by more and more data. Probably there is a lot to be done in the field. Okay, so I wanted to finish with this. It's more related to experiments, and I think it's interesting because the field is moving very fast now. Okay, so let's stop here.